We are now in classwork 4.4, and we are graphing polynomial functions today. So first of all, x-intercepts, whether you are talking about polynomials or any other function, they are the values where the graph crosses the x-axis. Okay, you can always watch the video notes later. I've got to keep going. And then also it's a point where y is equal to 0. And that's the key to finding them, is understanding that they are where y is equal to 0. You've got to know some vocabulary words, and that one of them is zeros. X-intercepts are called the zeros of any function, not just a polynomial function, but we say the zeros. So if they happen to be where y is equal to 0, and I ask you to find the x-intercepts, then you're going to take your polynomial function, you're going to set it equal to 0, and you're going to solve that equation. In the homework that was due previously, you were solving equations for polynomials. You were looking at what makes them equal to 0. All you're doing as a pre-step before number 17 and 18 from your homework is actually putting equals 0, and then you are at this spot. And then going back over there. So know that that's how you're going to find your x-intercepts, and we're going to practice that in just a moment. Now, these x-intercepts, these zeros, have multiplicity, and this is a word that you've got to become familiar with right now. So if you saw what I just highlighted, how else might you write that? Correct. And crosses the x-axis. Now, taking a little bit further, I now have that and a little bit more. So I'm going to highlight that I have this as well as what I previously had written. How would you write this in a more simple way? So you just write down how many times that particular factor is showing up and multiplying. Now, the zero of each linear factor has a multiplicity. Okay, can I spell right now? Multiplicity. There we go. And basically, it's just the number of its exponent. So the polynomial that we were just looking at if I asked you for q of x right here, if I asked you what are the zeros, what would your answer be for the zeros of that polynomial? I'm looking at chat. So the zeros, correct. The zeros are what solve the equation for when you set it equal to 0. And remembering back to your homework that we've had so far, when you've factored a polynomial and it's set equal to 0, in order to solve that equation, you set each individual factor equal to 0. But what's the square root of 0 and the cube root of 0? They're just going to give you 0. So when you're solving for what makes each of these factors equal to 0, you can go into just the linear factor that has the exponent on that linear factor. Just go into that linear factor. What makes x minus 1 equal 0? And what makes x minus 5 equal to 0? So that polynomial has zeros 1 and -5. And we say the multiplicity of 1 is, hold on, I'm trying to figure out what I should erase to show this a little bit better. I'm going to kind of get rid of all those highlights. So we are looking at this polynomial right here. The 0, 1 is coming from the factor x minus 1. The exponent there is a 2. So we say the multiplicity of 1 is 2. And then we can also say that the multiplicity of -5 is, and what do you think? What will we say the multiplicity of -5 is? Good, 3, the exponent on that linear factor. This is very important for graphing polynomials. Know that in this class, you're not going to get to a point where you can graph just any old polynomial that shows up. I'm only going to expect you to be able to graph polynomials that are factorable into linear factors. Because anything other than that, the only way you're going to factor it is with a whole bunch of point plotting, which you can do anytime. What I want you to learn is how to graph beyond point plotting. So, in preparation for what we're about to look at, what are the zeros on number 1 for f of x? What are the zeros for f of x? Okay, yeah. Go ahead and leave and rejoin. That's fine. And I'm looking at chat. What are the zeros of the polynomial for number 1? So it looks like you guys aren't quite sure. What you're going to do is take each linear factor that has a power, write that linear factor equal to 0. So linear factor x that is being squared and linear factor 2x plus 5. Yes, as far as the quiz goes, I'm going to give you the quiz today that I was going to give you Friday, which is 4.1, and I will talk about that right before we go into it. But I did talk about it Friday, and I feel like that gave you time to be aware and study, maybe. So what makes those polynomials, those linear factors equal to 0? And I saw negative 2.5, and that is correct. And also 0. And I'm getting negative 2.5, or you can say negative 5 halves, by solving this equation. Now, what is the multiplicity of the 0, 0? Love the overuse of words. Correct. The multiplicity is the exponent number on the factor that created that 0. So 2 is the multiplicity of 0, 0. What is the multiplicity of 0, negative 2.5? You got it, 3. And just know that I set these charts up with more room than necessary for the possibility of there may be polynomials coming with more zeros than just 2. Then, number 2. What are the zeros of g of x for number 2? What are the zeros for g of x? So make sure you're looking, are you looking at g of x right here? And g of x is written in its factored form, right? You're looking at what makes x plus 6 equal 0, good. And then what makes x minus 8 equal to 0. And that will give us negative 6 and positive 8. Now, I don't see an exponent on x plus 6. What does that mean? Correct. There's an understood exponent 1. So if you have a linear factor that is a lone linear factor, we call the multiplicity of that 0, 1, multiplicity 1. And then what is the exponent on the x minus 8 factor? And I'm waiting for an answer. There we go. Thank you. And that means that 8 has a multiplicity of 2. Now, before we go into graphing those, I'm going to talk to you about what this tells us. On Friday, you learned a bit about the end behavior issues of graphs. Now we're going to talk about what we can do with the interior if it's nicely factored into linear factors. Okay. So let's see, what did I intend to have written there? Oh, each x-intercept of a polynomial graph is a 0 of that polynomial. And I want you to be aware that the behavior of that 0, sorry, I just realized I had behavior there. Silly me. My apologies. And now you have imperfect work. The multiplicity of that 0 determines how the graph behaves at that x-intercept. And here we go. I have 3 polynomials written down. All 3 of them, I am focusing on a particular 0. There are more zeros than just 5 on all of these polynomials, but I wanted to focus on just one of them and talk about it. I want you to see that for the first p of x polynomial, the 0, 5 has multiplicity 1. For q, the second one, I have a multiplicity of 2. And then for r, the third one, I have a multiplicity of 3 for the 0, x equals 5. And we're going to look at these graphs. And I'm going to circle I'm circling x equals 5, and I want you to take a really good look at the 3 of them. When the multiplicity is 1, it just slices through the x-axis, just ooh, like a ninja. Oh, what was that, Fruit Ninja? Were you swiping it? Yeah, okay, never mind. When the multiplicity is 2, realize that when you square something, you force it to be positive. So that means that where a multiplicity of 1 and a multiplicity of 3 allow for a sign change to happen at x equals 5, that even multiplicity will not allow a sign change. The graph will bounce off the x-axis because it is unable to change from a negative to a positive or vice versa. But if I go up to multiplicity 3, it doesn't just slice through. And I put a word in the notes that would just sound better for you guys. I could give a more technical word and say it has an inflection point. But it's kind of like going, ooh, like it wiggles or it does the worm dance. When you have an exponent of 3, when the multiplicity is 3, and what I want to point out to you is, actually, let me go over to the answers now. I want to point out to you that when the multiplicity is 1, it slices through similar to y equals x slicing through the x-axis. When its multiplicity is 2, it bounces off the x-axis like x squared bounces off the x-axis. And when the multiplicity is 3, it kind of wiggles or has an inflection point through the x-axis, similar to the way x cubed does. And if I continue to go up in multiplicity, do you see the pattern? If my multiplicity is 4, then it's going to bounce off more like x to the 4th, and that's a terrible drawing, but I'm hoping you get the idea. If it's a multiplicity 5, it's going to wiggle through, but it'll be a tighter wiggle, shall we say. It'll be a scrunchier wiggle, but not that that is something you need to be able to compare. Basically, if it has an even multiplicity, it's going to bounce off the x-axis. If it has an odd multiplicity, it's going to go through the x-axis. But if that odd number is 3 or larger, it's going to wiggle its way through. So the differences between the odd and the even multiplicity, and important that you understand that when you have that odd multiplicity, the y value of your polynomial is allowed to go through a sign change. But if it's an even exponent, it will not go through a sign change. It'll stay positive or it'll stay negative. And I'll give you a minute to write that down. And then, wait, Lucas, I just saw your question. Did I answer that question already? The way I look at it is the factor acts a little bit like its lone self when you're near the x-axis. So if you have a multiplicity of 1, it behaves closer to a line than other polynomials. When the multiplicity is 2, it looks a lot like x squared when you're near that x-intercept. If it's multiplicity 3, it behaves a bit more like x cubed when you're near that multiplicity, that x-intercept. And I want you to know that as far as graphing polynomials goes, this is really about as far as you can go at this point, is just understanding how it behaves near the 0 and bring that together with the end behavior. And you can graph a reasonable version of polynomials as long as they're nice and factorable. If you have a polynomial that you cannot factor into linear factors, I feel like it's better for you to wait to deal with that until you have tools that can deal with it easily. Otherwise, it's kind of a waste of time to point plot when technology will do it for us. You don't need to point plot like your ancestors did. And by ancestors, I mean your parents and grandparents. What I want you to be able to develop is some graphing sense skills. Yes, you've got technology that's going to instantly tell you what things look like, but it's valuable for you to understand the relationship of an equation and a graph. But for you to have to sit there and point plot to be able to draw something that technology can draw for you, it's kind of antiquated to bother with that once you know how to point plot. So, moving on. Okay, so you're looking at the graph of a polynomial function. Now, take a look at it. Show me the end behavior with your arms. Let me see that end behavior. Let me see the end behavior with your arms. In other words, yes, you're riding a roller coaster. Woo! Remember how that used to feel, riding a roller coaster? Actually, they've opened up places, haven't they? I would fear to ride on a roller coaster right now, I've got to say. I would not go after someone. I don't care how much they disinfect. Anyway, moving on. What does this tell you about the equation? With it going up, what can you expect from the equation? It has an even exponent. So it is an even degree polynomial. And what does it tell you about the leading coefficient? What does this graph tell you about your leading coefficient? If the right end goes up, your leading coefficient is what sign? Not remembering? Yes, yes. Your leading coefficient is positive. Now, let's take a look over here. What I just highlighted there, I'm going to erase the other highlight. What I just highlighted, what does that tell you about the factored form of your polynomial? You got it. That is exactly it. And what is the factor that will create -5 as a 0? So what expression do I put in here so that when I set that number equal to 0, I get x equals -5, x plus 5. So if you're trying to figure out which of those multiple choice answers goes with this graph, you know that you've got to be finding a factor of x plus 5, and it needs to be either a 3, but it also could be a 5 or a 7, but it's an odd number that's 3 or larger. Ah, yes. And then, so you see over here that means you have x minus 3 is one of the factors. It's what creates positive 3 to be a 0. And it's squared, or maybe it's to the 4th power. That is a possibility. And then do you see any other x-intercepts? Anyone see another x-intercept? Yep, right there. Now, with that x-intercept, what has to be a factor? What has to be a factor of this polynomial so that it goes through the x-axis at x equals 0? Like we got these factors. What does this one tell us is one of the factors? So maybe what is set equal to 0 so that the answer I get is x equals 0? It's almost too plain. So when I say a factor, I mean use the variable x as you say it. What has to be a factor? X. And do you see that it definitely has a multiplicity of 1 because it just slices through? We don't write the 1, but I'm going to temporarily write it just to emphasize. Now, know that if you have a factored form of a polynomial, All of these are showing factored form, and let me make sure to clarify. We've got a number up front here. After that, I have a factor that causes an x-intercept of 0, and that multiplicity is 3. This tells me that I have an x-intercept of -5 with multiplicity 3. And this says I have a 0 of 3, an x-intercept with multiplicity 2. All of these factors are written in a form of x and then plus a number or minus a number. What I don't have a number in front of my x. That's what I want to emphasize about these factors. If you have x leading every one of these linear factors in the interior, then what you can be guaranteed of is the front number is the leading coefficient. So all of these are showing a leading coefficient of 1 over 150. Is that a ridiculous number? I had to throw in a number that large in a denominator so that this wasn't so steep that you couldn't see it. Polynomials can be very, very steep. Now, here's one more thing that I want to tell you. Are you paying close attention? No. Okay, everyone, ride a roller coaster for a moment. Woo! Oh my goodness. And robotics, are you feeling the woo? Yeah. From Nick, little robotics roller coaster. Woo! All right. Are we back alive again? All right, let's pay attention. Listen. If you look at the multiplicity of each of your linear factors and you add the multiplicities together, you will get the degree of that polynomial. The degree of the polynomial is the sum of the multiplicities of its linear factors. So I'm going to write that over to the side. That's very important. The sum of the multiplicities of the linear factors of a polynomial, and mind you, this is only talking about ones that can be factored into linear factors. So if you are factored as only a bunch of linear factors, the sum of the multiplicities is the degree of the polynomial. And you could say that the degree of the polynomial is equal to the number of linear factors if you were to write them all out as I had at the very beginning of the classwork. But again, I want to make sure to clarify that this is only if you're dealing with polynomials that can be factored into linear factors. We're not going to deal with things with irreducible quadratics. I feel like it's a bit of a waste of time at this level because you have to point plot. And it's the only way you can really figure out what's going on. And there are better ways to do it when you learn more math. So for each of these, I'm wanting you to explain what's wrong. Which one is the one who could be that graph? And with the other ones, why could they not be? So which one is the right one? Which one has all of these features? Do you guys agree? Letter D has all of those features. Now, I want to make sure that you're clear. What could you say makes number one not correct? What about, or did I say number one? Letter A. What about letter A makes it not the right one? That x cubed. If that were x cubed, then it would have to do some wiggling through the x-axis, and it's not doing that. So that is not going to be the correct answer. Then let's go on to B. What is wrong with B for this being its graph? What is wrong with B? Right. That x plus 5 is not cubed. If x plus 5 had was showing a multiplicity of 1, then it should be slicing through, not wiggling through. And then lastly, C. What is wrong with C? Yep. X minus 3. It's bouncing off the x-axis at 3, so that has to have an even exponent, 2, 4, 6, 8, something like that, but certainly not an odd exponent. And I want to also point out to you, for letter A, what is the degree of the letter A polynomial? And this is going to help you if you stop and do this right now. What is the degree of that polynomial? Correct. Just add up those exponents. 3 plus 3 plus 2. So that one is showing an even degree. That made it have some greater likelihood. What is the degree of the polynomial for letter B? What is the degree of letter B? The degree is 4. You have an understood 1, an understood 1, and then a 2. Oh, good grief. Okay. My 5-minute alarm just went off, which means I'm done with you. And what I'm going to do is I'm going to make a second recording where I finish talking through the rest of this, but I've gotten through with you the main part that you need to know to get you through the homework. So I'm going to finish this recording